Across the globe, towering monuments to human ingenuity stand as testaments to civilization. Yet, while many modern structures begin to crumble within decades, built with the very best of our current technology, others, crafted thousands of years ago, endure. From a majestic Pantheon to the mighty Colosseum, the edifices of ancient Rome defy time itself. How did a civilization, lacking our advanced materials science, construct buildings that still outlast our contemporary marvels? This is the enduring mystery of Roman concrete, a lost art that continues to perplex and inspire, hinting at a forgotten wisdom far beyond our understanding. Imagine the magnificent structures of Rome, standing proudly for over 2 millennia. The Pantheon's dome, a feat of engineering, remains the largest unreinforced concrete dome ever built. Roman aqueducts still carry water, and their harbors, submerged beneath the waves, continue to resist the relentless assault of the sea. Contrast this with our contemporary concrete, which often requires significant maintenance or even replacement within a mere 50 to 100 years. The stark difference begs a crucial question. What ancient secret did the Romans possess, allowing their creations to mock the very concept of decay? The Romans called their revolutionary building material opus cementitium, a term that translates roughly to cement work. But this was no ordinary cement. Unlike simple mortar, this was a composite material, the ancestor of what we now know as concrete. Its invention freed Roman architects from the constraints of cut stone, enabling them to construct colossal vaults, arches, and domes with unprecedented speed and scale. It was a material that fueled an empire, allowing them to build an infrastructure network that connected vast territories and endured for centuries, creating a legacy that baffles engineers even today. To appreciate Rome's achievement, we must understand the weaknesses of modern concrete. Our version, typically made from Portland cement, sand, aggregate, and water, is strong but inherently vulnerable. It's prone to cracking due to temperature changes, and crucially, water infiltration leads to corrosion of the steel rebar within. This expansion of rusted steel creates internal stresses, causing concrete to spall and crumble, necessitating costly repairs and shortening structural lifespans. This vulnerability highlights the profound difference in the Roman approach. The first, and perhaps most critical, ingredient in Rome's enduring formula was pozzolana, a fine, reddish volcanic ash found near Pozzuoli, Italy. This seemingly ordinary dirt possessed extraordinary hydraulic properties. When mixed with lime and water, it didn't just dry. It reacted chemically, creating incredibly strong, water-resistant bonds. This wasn't merely an aggregate. It was a fundamental component that transformed the very nature of the concrete, imbuing it with qualities that would define Roman engineering excellence. While pozzolana was unique, the Roman treatment of lime was equally vital. Instead of simply mixing quicklime, calcium oxide, with water to form a paste, evidence suggests the Romans used a hot mixing technique. They would combine quicklime directly with pozzolana and aggregate, and then add water, allowing the chemical reactions to generate significant heat. This intense heat created a more reactive and homogeneous binder, leading to a denser, more resilient concrete that cured stronger and faster, embedding microscopic mineral structures crucial for its longevity. For their most demanding projects, like harbors and marine structures, the Romans added another layer of genius: seawater. This wasn't a mere convenience. It was a deliberate choice. The salts and minerals within seawater, when combined with the pozzolana and hot mixed lime, triggered unique long-term chemical reactions. Instead of weakening the concrete, seawater actually fostered the growth of complex, interlocking mineral structures over time, making the concrete denser and virtually impervious to degradation, a stark contrast to how seawater devastates modern concrete. Beyond the binder, the aggregates played a role. Romans often incorporated stones, ceramic fragments, and even brick shards, which were porous and reactive, enhancing the concrete's overall strength and durability. The combination of pozzolana, hot mixed lime, and these specific aggregates created a highly cohesive matrix. This wasn't just a haphazard mix. It was a carefully calibrated system designed to interlock and bond at a microstructural level, ensuring that the entire composite material worked in harmony to resist external forces and internal stresses. Perhaps the most astonishing discovery about Roman concrete is its potential for self-healing. Researchers have found that tiny cracks, rather than expanding, can actually seal themselves over time. This remarkable ability is attributed to the presence of specific aluminum-rich minerals, like stratlingite, which can grow within microfissures when exposed to water. This means Roman concrete wasn't just designed to endure. It was engineered to repair itself, a biological resilience built into an inorganic material, a truly revolutionary concept even by today's standards. The Roman harbors, constructed from this miraculous marine concrete, are perhaps the most compelling evidence of its superiority. Submerged for millennia, pounded by waves, and exposed to corrosive salts, these structures show minimal erosion. Modern concrete rapidly degrades in similar conditions, but Roman piers and breakwaters actually grow stronger, forming crystals like tobermarite and philipsite, which increase density and bond strength. These underwater marvels prove the Romans truly mastered the art of building to last, even against nature's most relentless forces. Today, scientists are feverishly working to reverse engineer Roman concrete, hoping to unlock its full potential for modern applications. Imagine a future where infrastructure lasts for centuries with minimal maintenance, where construction is more sustainable, and where materials can repair themselves. The study of opus cementitium is not just an academic exercise. It's a profound lesson in material science, offering sustainable solutions and a humbling reminder that sometimes the most advanced technology is found not in the future, but in the echoes of a glorious past waiting to be rediscovered. The enduring legacy of Roman concrete is a powerful testament to human ingenuity and the wisdom of observing nature's own materials. While we marvel at their architectural grandeur, the true marvel lies beneath the surface, in the intricate chemistry and ingenious methods that allowed them to forge structures that truly stand the test of time. Their secret, a blend of volcanic earth, carefully treated lime, and perhaps even seawater, offers us a blueprint for a more resilient and sustainable future. The ancient Romans built not just for their generation, but for millennia, leaving us with a challenge: to learn from their undying stone and build a legacy worthy of their enduring vision.